Hello, this is Dr. Gardner. We're continuing to classify chemical reactions, and in part 3 today we'll be looking at acid-base neutralization reactions. We'll be looking at precipitation reactions, which are double displacement reactions for both of those. We'll also look at gas evolution reactions, which can be considered in many cases to have multiple steps. Some could be categorized as double displacement, some could be categorized as decomposition, and then we'll see gas evolution occurring as well. And then with respect to these types of reactions, we're going to apply a new technique. This new technique we're going to apply, we'll be writing net ionic equations. So we'll learn the steps in order to do that. Now, I am assuming you've watched the previous tutorials on classifying types of reactions, and I expect that you've learned your solubility rules. If you're still working on your solubility rules, you may find it helpful to have your notes or your handouts on your solubility rules, or open your textbook to the table on solubility rules. Now, something you should watch is some of our videos on strong, weak, and non-electrolytes that I've included in our schedule. I'd recommend watching those first because they'll help explain in our net ionic equations as to which spectator ions we'll be removing. We'll be looking at what spectator ions are here in a moment. But first of all, let's go ahead and review double displacement reactions briefly. If you remember, our double displacement reactions have a form similar to CD plus EF yields CF and ED. So our analogy was we were relating a barn dance, and if these were ionic compounds, let's say forming a precipitation reaction, we might have a cation and an anion pair, and then a second cation and anion pair, and then the cations and anions swap partners, and then we end up with a new set of ionic compounds. And if one of the new ionic compounds is insoluble, we expect to predict a precipitation reaction. Now, if every product was soluble, we'd expect no significant reaction. There was really no change in the solutions you were looking at. So we'll be comparing those today as we write our net ionic equations. Now, when I do look at double displacement reactions, precipitation reactions are considered double displacement. Some types of gas formation reactions will have a step that involves double displacement, and acid-base neutralization reactions will also be considered double displacement. So those are the main types of double displacement reactions we'll be looking at today. First of all, make sure that you're learning your solubility rules for ionic compounds. I will expect you to have this memorized before our next exam. Now, something you'd realize is that there are many types of ionic compounds that are present in the world around us. Many soluble ionic compounds, like sodium chloride table salt, and many other types of soluble ionic compounds can be present in water systems. Like your drinking water, you can have small amounts of soluble salts, or if you consider ocean water, you can have large amounts of a variety of soluble salts. However, when you start looking at the minerals around you, the minerals around you are also made up of ionic compounds, but usually these minerals are fairly insoluble and they don't dissolve readily, for example, when it rains. These types of minerals are made up from anions present with cations that produce insoluble compounds. Now, the most common types of anions that will produce insoluble compounds found in the minerals and the rocks around us would be sulfides, so metal sulfides, metal phosphates, metal carbonates, and metal oxides. So, for example, let's look at a few of these. Azurite is a copper carbonate compound. That's a mineral. We can also look at iron pyrite. This is a type of iron sulfide precipitate. And we can look at arsenic sulfide. So we're seeing sulfides and carbonates. We could see phosphates frequently, or oxides. Those are all examples of insoluble ionic compounds that we can find in the minerals around us. So if you decided you wanted to go into geology, you're going to be looking at ionic compounds that in many cases are fairly insoluble. For example, when you think about limestone or marbles, frequently there are carbonate salts present there, such as calcium, magnesium, and iron carbonates present in those types of substances. Now, when I think about ionic compounds occurring in the chemical laboratory, frequently we'll mix solutions that contain soluble ionic compounds, and one of the ions present may precipitate out with the ion from the second solution we may have mixed to form a precipitation reaction. So when we mix multiple ionic solutions and we form a combination of ions that's insoluble, we form what's called a precipitate. This is going to be an insoluble solid that separates from our solution. So let's look at an example of this. I'm going to take a solution of lead 2 nitrate and sodium iodide and mix these two solutions. So if I mix lead 2 nitrate which is soluble because of the nitrate ion. All nitrate salts are predicted to be soluble. And if I mix that with a second solution of sodium iodide, well, sodium salts are soluble. But however, when I mix these together, there's a chance for the lead-2 ions to come in contact with the iodide ions, which we know from our solubility rules would form lead-2 iodide as a precipitate. So I'm going to show a solid for the phase label. Then I also produce sodium nitrate, which is a very soluble ionic compound. So I've labeled here on both sides of the reaction arrows every combination that would be soluble. So lead-2 nitrate is soluble, so I show an aqueous phase label. Sodium iodide is soluble, so I indicate that it's soluble with the phase label. Lead-2 iodide is a precipitate, so I show a solid for the phase label. And sodium nitrate is very soluble, so I indicate that it's in solution. Now, if I show all of my ionic compounds together in formulas that do not have the ions dissociated. But what I mean by dissociation is I have not shown the ions separated, indicating they would be separated in the water-based solution yet. When I write my ionic my ionic compounds forming a precipitate in this precipitation reaction, this is called a molecular equation, even though I have ionic formulas. All it is indicating is that I've shown all of the ions together, even if they might dissociate in solution, even though they might produce ions as water molecules separate cations and anions from the solid. Now I can break up all the soluble ionic compounds and indicate which ones are being surrounded by water molecules by writing the total ionic equation. The total ionic equation will show all the soluble ionic compounds here. So if I show my total ionic equation, then we can realize that we have lead-2 ions, nitrate ions, sodium ions, and iodide ions in solution. And normally I would add phase labels to those that said aqueous. For the sake of how long this reaction would be on this slide, I haven't added the aqueous phase labels, but you could go ahead and do that to every ion here that is dissolved. Now I have shown the precipitate, and I want you to notice that the precipitate here, lead-2 iodide, is indicated with a solid after it in the phase label, and we do not break up the ions of precipitates in total ionic equations. In fact, in all of the equations I'm going to show you on this slide, the precipitate, the lead-2 iodide, should be shown together in its original formula. Now, once I look at all of the ions, which have separated by being surrounded by water molecules from their ionic species, we can decide that a few of them aren't changing. So if we look at the sodium ions, I have sodium ions on both sides of this equation. And if I look at the nitrate ions, I have nitrate ions on both sides of the equation. However, my lead-2 cation here and my iodide ions, they have changed their situation. To begin with, the lead-2 ions were surrounded by water molecules in the water-based solution. The iodide ions are surrounded by water molecules in the water-based solutions. When they ran into one another, they ended up usually precipitating to form lead-2 iodide as a solid. So that's where I'm seeing the change for this chemical reaction, the precipitation reaction in this double displacement process. I am not seeing any change for the nitrate ions or the sodium ions on either side of the equation, so they really weren't so important for this chemical reaction other than balancing charge in the original solutions of lead-2 nitrate and sodium iodide. So when you see these ions that are just there before and after a precipitation reaction like this, we can call those spectator ions. In a sense, they're kind of like spectators at a sports game. They don't really have much of an influence on what's changing with respect to the sports game on the field. So you can imagine if the lead-2 ions were running out to accept a thrown football, and your iodide ions were running out to tackle them, and we ended up with lead-2 iodide as the dog pile that occurs as we get a tackle, and we end up with precipitate forming. Well, there's something interesting occurring, something interesting that's changing. But the sodium ions and the nitrate ions, they're just kind of hanging out watching the sports game in the field, and they don't really have anything changing. Their lot in life hasn't changed here, and so we're going to call those spectator ions. And what I want to do next is write what's called a net ionic equation. To write the net ionic equation, I will remove the spectator ions. So I'm indicating that I've canceled the nitrates and sodium ions out as spectator ions, and so I've listed sodium and nitrate ions as spectator ions. And my net ionic equation shows me really what has changed in the chemical reaction, where I have lead-2 ions precipitating with iodide ions, so I would add a phase label AQ here, indicate they were soluble to begin with until the lead 2 ions came in contact with iodide ions, and then quite a few of them would end up precipitating, and we end up with having a product that was the lead 2 iodide precipitate, so indicate the solid for the phase label. You notice that the precipitates in all three reactions that we've written, the molecular equation, the total ionic equation, and the net ionic equation, we show the precipitates always together because they are not significantly separated by the water molecules dissolving this compound. So on a test, I will usually give you the solutions that we were mixing. So I might say lead 2 nitrate is being mixed with sodium iodide, and I might ask you to predict the products from knowing your solubility rules. To predict the products, I just try a new combination of cations with anions. So I'd write down lead 2 iodide, sodium nitrate, and predict from solubility rules that the lead 2 iodide would precipitate and the sodium nitrate would be soluble. For writing the total ionic equation, which I would also ask you to write on a test, I would go ahead and take every strong electrolyte, so in this case every soluble ionic compound that we have, and I break it up into ions. Now I would definitely on a test write phase labels. I do want you to write phase labels. I just didn't label them all here for the sake of space, so I would write AQ for all of my soluble salts. Now on the exams I also have you indicate which are spectator ions. So I might have a line where I ask you to list the spectator ions like we did here below. Just realize I would remove those spectator ions from the total ionic equation to write the net ionic equation. And so all I will see are the cations and anions that are present that would form the precipitate that we now have a change. So really the net ionic equation is going to be a summary of everything that's going on. We don't really care about the spectator ions because they didn't change what they were doing in solution from the beginning to the end. The sodium ions and the nitrate ions were surrounded by water molecules and dissolved to begin with. They were surrounded by water molecules and dissolved at the end of the process. So really they weren't critical in describing anything changing. So the net ionic equation just summarizes the most important changes in this chemical process that we are looking at. So that's just something to be aware of. With respect to these, we'll be writing net ionic equations for precipitation reactions. Now I have been known to give ionic compounds that are completely soluble when mixed together with no precipitate. If that's the case, you want to show no reaction, and there will not be a net ionic equation in that case because everything would be spectator ions if no reaction occurs, if everything were soluble, even with the new possible cation and anion pairs. So make sure you look for that. Now, what we can also use net ionic equations for are looking at other types of double displacement reactions. We'll apply them to looking at acid-base neutralization processes. We'll also apply them to looking at gas evolution processes here in a little bit. Realize that when we start looking at net ionic equations, whatever you are not breaking apart is either a insoluble solid, a non-electrolyte, or a weak acid or base. So realize anything that isn't a strong electrolyte, then we do not want to break apart into ions. So a weak acid or base we show in its molecular form. A strong acid or base, which is a strong electrolyte, we would break up into its ions. A soluble ionic compound we would break up into its ions. An insoluble ionic compound we would show together in its formula. So anything that is not a strong electrolyte, do not break up into ions. Anything that is a strong electrolyte, please break up into the ions. Okay, so here's my steps for writing a net ionic equation just in review. You want to write a balanced molecular equation to begin with. Then you want to determine, if it's a precipitation reaction, what insoluble compounds might form. So I have to know my solubility rules, so hopefully you're quizzing yourself. Maybe you have some index cards you're quizzing yourself with, or an electronic program that you're using on your smart devices to quiz yourself as an application. Or we could also end up with having other reactions. So if I have a reaction other than a precipitation reaction, let's say we have acid-base neutralization processes, we'll predict the other products that might form from the reaction. Then what we'll do is write the total ionic equation showing all the ions that are occurring from any strong electrolytes. So any strong acids, any strong bases, and any soluble ionic compounds should be broken up into ions. If I have a weak acid or a weak base or a insoluble ionic compound as a precipitate, we would show those together and not break up the formula. Now once I've written the total ionic equation, we'll want to look for any spectator ions that are present on both sides of the equation. If there are any spectator ions present, we would want to go ahead and cancel those out and just write the ions that are changing with respect to the process. So we'll show those ions and the products that are forming, and that will be the net ionic equation. And oftentimes I will have you list the spectator ions that you remove specifically on an exam, so be ready for that. So let's practice writing some net ionic equations. First of all, let's consider the reaction between silver nitrate and sodium chloride. So if I look at this chemical reaction, I can recognize that nitrate salts are very soluble, so I'm going to show a phase label of AQ here to indicate the soluble silver nitrate. I also recognize that sodium salts are very soluble, and chloride salts are very soluble, except for a few exceptions. So I'm going to show AQ, so I have soluble ionic compounds in solution to begin with. If I mix these two solutions and I want to predict if there's a reaction, we show the reaction arrow to the right, and then we show our new possible products. So I could have the cations with new anions. I don't try to place cations together. Their positive charges would repel. I don't try to place anions together. Their negative charges would repel. So I only get new cation-anion pairs. So I could get the silver cation with the chloride ion potentially. So I write the other possible combination. Remember, this is a double displacement process potentially. So everybody's switching partners like a barn dance. So we end up with silver paired up with the chloride ion potentially. So silver's a +1, chloride's a -1, so I just need 1 to 1 there. I show a plus sign before the next possible product. I show the sodium cation paired with the nitrate ion. And then I think about the solubility of the products. Now sodium's a +1 and nitrate's a -1, so I also need just 1 and 1 there. Everything's balanced. It's a very simple reaction, so coefficients of 1 have this entire reaction balanced, but I'd always want to check that. If I look at my solubility of the products, well, the sodium nitrate's very soluble. Sodium salts we predict to be very soluble, nitrate salts we predict to be very soluble, and so I'm going to show a phase label that these are dissolved in solution. It's a strong electrolyte solution, aqueous. Now the chloride salts are frequently soluble, but not when they're mixed with silver cations or lead-2 cations or my mercury 1 cations. So we end up with having, in this case, a precipitate, a solid precipitate that forms. And so that I know this reaction occurs because I form a precipitation as a product. I end up with an insoluble compound. And so in this case, this is the following molecular equation. So we've just written the molecular equation. Even though these are ionic compounds, it just indicates I haven't broken up anything into ions yet. So this is the molecular equation. Now the next equation I want to write will be the total ionic equation. So my total ionic equation, I'm just going to write TIE here for a total ionic equation. Go ahead and write the whole thing out on your notes. So the total ionic equation will show any soluble ionic compounds as broken up into ions. So the ones we want to break up into ions are going to be the soluble silver nitrate, the soluble sodium chloride, and the soluble sodium nitrate. Those are going to be strong electrolytes in solution, so we show them as ions. So I have my silver cation with a phase label, and then I have my nitrate ion with a phase label, just breaking up all the soluble ionic compounds. And what I'm indicating here is that these ions are surrounded by water molecules and usually separated from one another in solution. And so I have silver cations, nitrate ions, sodium cations here. I'm going to have chloride ions. So to begin with, before the solutions have had a chance to mix, we end up with all the ions present in solution until they start to swap ion pairs to potentially form a precipitate. Now anything that is a non-electrolyte or a weak electrolyte or a precipitate we keep together. So when I show my products, I'm going to show the precipitate of silver chloride together. I do not break it up because the silver cations and the chloride ions are part of an ionic lattice. They're together in very close proximity. Sorry, there should be no charge there. So no charge on this. And then we end up having the other products are the sodium nitrate, which is soluble, so I show that broken up into ions. So the total ionic equation will show everything that's soluble or a strong electrolyte broken up into ions, and everything that's insoluble or a weak electrolyte shown together as the initial formula, indicating that those atoms or ions are in close proximity with one another. So this would be a correct total ionic equation. Now what I want to recognize is if there's any spectator ions. So if I want to list my spectator ions, I'm going to put Si down here for spectator ions. I look for the spectator ions as the ions that have not changed what they're doing in the chemical reaction. So if I look at the sodium ions are not changing, and the nitrate ions are not changing in this chemical reaction. So I would say my spectator ions are sodium ions here and nitrate ions. So I list my spectators down here. Those are the ions that are spectating, that are not involved in the chemical reaction. So when I write the net ionic equation, so NIE for net ionic equation down here below, when I write the net ionic equation, I'm going to remove all the spectator ions. So I'm removing nitrate and sodium. So I say basically if I have silver ions from any soluble ionic source reacting with chloride ions from any soluble ionic salt source, the important reaction that's occurring here, the change in the solution that would be occurring, is that the silver cations will react with the chloride ions to form my products. And so my products are going to be the silver chloride precipitate. So you'll notice that the silver chloride precipitate, since we have those ions in close proximity in the ionic lattice, in the precipitation product as we form our solid, they're always written, the precipitate is always written together. Sorry, this should have been a phase label of an S there for a solid. My mistake. And then I end up showing the silver chloride precipitate together all the way through all three of my equations. The net ionic equation just excludes any spectator ions, and it tells me a summary of everything important that's changing in this chemical reaction. Okay, let's keep practicing this. Let's consider the following net ionic equation that we want to write. So this reaction we're looking at now is potassium chloride plus rubidium nitrate. We're considering as we mix these two what might be occurring. So my possible products could have a new combination of cations and anions. So let's go ahead and look at potassium cation paired up with the nitrate ion. So I could have potassium nitrate as one product. And I could have rubidium chloride as another product. Then what I want to do is look at the solubility of everything and use my solubility rules. So potassium salts, remember my alkali metal salts are very soluble. So potassium chloride is soluble, so I show a phase label AQ. Rubidium nitrate, well, rubidium is an alkali metal, so I expect it to be soluble, and nitrate salts are very soluble, so I'm going to show AQ. And then I have potassium nitrate. Potassium nitrate is a very soluble salt. Potassium salts are soluble, nitrate salts are soluble. AQ. Now rubidium salts we expect to be soluble. Chloride salts are usually soluble, but there's some exceptions when we're dealing with silver, lead, and mercury. Since I don't have silver, lead, or mercury here, this one is also soluble. What that tells me is if I were to stop and write the total ionic equation, every single species here would be broken up into its ions. They would all be spectator ions. We didn't form any precipitate here at all. If this was a situation that you had, which can occur in lab, I can definitely mix these types of solutions together in lab, we wouldn't expect to see any solid coming out of solution. So there's no reaction occurring. So if you just write NR in a situation like this and tell me there's no reaction, I understand that you understand your solubility rules and that you predicted there's no significant change once mixing these solutions. All the ions are surrounded by water molecules to begin with. They're all surrounded by water molecules at the end of the process. Nothing ends up coming out as a precipitate. And I have been known to give reactions like that on the test, so be sure that you can recognize when there is and when there is not a precipitation reaction. The next type of reaction we're going to look at is acid-base neutralization reactions. So once we understand if I have an acid-base neutralization reaction, we look for an acid reacting with a base. This is why I had you at the very beginning of the course start memorizing your strong acids and strong bases and trying to recognize other types of acids and bases. Now, the products that usually form with your acid-base neutralization reactions that we're looking at, we usually end up with a salt. So we get an ionic compound that has a cation that came from the base and an anion that came from the acid, and then we end up having the other product is frequently water. So if we're looking at a lot of the acids and bases in Chem 101 that we tend to focus on, I see an acid mixed with a base forms a salt and water. So those tend to be the products. So I can imagine the acid, most of our acid formulas in Chem 101 have an acidic hydrogen at the beginning of the formula. Acetic acid, sometimes we'll write that slightly differently with the acidic hydrogen at the end, so just be aware of that. But frequently I see an acidic hydrogen and acidic proton that can be lost to in a water-based solution with an anion, and then we end up with a base which frequently will have a cation paired with hydroxide. So when I form my product, I could end up with the cation, as I said before, from the base and the anion from the acid, and then I end up with the acidic proton, the basic hydroxide forming HOH, which is better known as water, H2O. Okay, so just remember, we predict the anion coming from the acid and the cation from the base when you're predicting products here. So let's compare this to a reaction and write a molecular equation, a total ionic equation, and a net ionic equation. Now remember, weak acids and weak bases, we do not break up into their ions in the total ionic equation. It's only strong electrolytes you should break up into ions. So strong acids, strong bases, and soluble ionic compounds. Okay, so let's consider the following reaction. We're going to mix hydrochloric acid with potassium hydroxide and predict the products and write all of our equations. So for my molecular equation, I'm going to write ME here for molecular equation. We're going to have my acid, so I need the correct formula for hydrochloric acid. It's HCl. Okay. And I'm going to predict all of my acids and bases are soluble, so I put aqueous. Okay, and then I'm going to have my base, my potassium hydroxide. Now hopefully I recognize that potassium hydroxide is a strong base and that hydrochloric acid is a strong acid. So I have a strong acid and base reaction here. And so I'm expecting an acid-base neutralization reaction, and I'm also expecting that the strong acid and strong base are strong electrolytes, meaning that they ionize readily. They form nearly 100% ions from their formula, so I'm going to break them up in the total ionic equation here in a moment. Now the products, as I said, when I'm looking for products of acid-base neutralization reactions, I look for a salt that is a combination of the cation from the base and an anion from the acid. So I would end up potentially with potassium chloride as one product. You notice this is a double displacement reaction. So potassium chloride is one product. The other product I could end up with would be the proton from the acid and the hydroxide from the base. So that would give me HOH, or you probably recognize it more readily as H2O, which is water. Now when I have water in a water-based solution, so if these are water-based solutions that I'm mixing and I'm forming water in a water-based solution, we do not put AQ as a phase label, we just put an L because I really don't consider it any different than the solvent molecule. So I just put it in the liquid state for my phase label. Now my potassium chloride, we'll want to go ahead and show potassium chloride as soluble because potassium salts are soluble, chloride salts are soluble unless there was silver, mercury, or lead, and so we end up with having aqueous for the phase label. Now, water is a non-electrolyte. It's a polar molecular compound, so I do not break it up into ions. Its major form is its molecule in solution. The strong acids, strong bases, and soluble ionic compounds in the total ionic equation get split up into ions. So for my total ionic equation here, and perhaps before, so my total ionic equation here, before I start to write my total ionic equation, I should make sure it's balanced. In this case, it was all 1 to 1 to 1 to 1, but realize not every chemical reaction will be balanced with coefficients all that are 1. If I break up all the strong electrolytes, so if I break up the strong acid into its ions, I end up with my protons, I would add a phase label like Q because it's soluble. Now, actually, in a water-based solution, we're forming hydronium ions, H3O+, by the proton being picked up by a water molecule. So I'm using a shorthand notation by only indicating it as H+ here, even though I know it would be attached to a water molecule in most circumstances. I also have my chloride ions, soluble, so I indicate the phase label that they're soluble. And on your homework, realize frequently for your online programs, what you're going to be seeing is the phase labels are usually not shown as subscripts. They're just in brackets after the formula. Our strong base, potassium hydroxide, is going to be shown dissociated here. And then I will have my hydroxide ion. And then what we'll see is we'll also form our products. Now we have a soluble ionic compound as a product, so I'm going to show it is dissociated in the total ionic equation because it's soluble. So I get potassium ions in solution. I also end up with chloride ions in solution. And then my water molecules are not forming any significant amount of ions here, so I'm going to show them together. So if I start looking at my total ionic equation for spectator ions, I want you to look at this. Which ions are not changing in this reaction? If we look here for unchanging ions, we're going to notice that the potassium ions are on both sides of the chemical equation, so they're spectators, and chloride ions are on both sides of the equation, they're spectators. So what I'm seeing is that the ions that are changing are my protons are combining with my hydroxide ions to form my water molecules. So I'd want to cancel out my spectators, and for the net ionic equation, so for my net ionic equation, NIE here, we're going to show that basically protons from any strong acid could react with hydroxide ions from any strong base. And as they react, we're going to neutralize the acid and the base to form water. So I expect this to be the net ionic equation whenever I have a strong acid with a strong base, because the spectators will be the cation from the base and the anion from the acid if they're strong acids and bases. So really, we've written the net ionic equation for all strong acid, strong base reactions. Now this will differ if I have a weak acid or base present, because if I had a weak acid, I'd have to have the undissociated acid formula written in here and the anion for the acid on the other side. Or if I had a weak base, I'd have to have the undissociated, unionized base on this side, and I'd have to show the cation on the other side. So realize with weak electrolytes, like weak acids or bases, we're going to go ahead and have to show them together. They are not in their major form shown as ions. But with strong acids and bases, here's your net ionic equation. So if I, for example, were mixing other strong acids, like if I was taking sulfuric acid and mixing it with, let's say, a strong base like sodium hydroxide, we'd expect to get a very similar net ionic equation. Okay, let's consider acid-base neutralization reactions that also produce gases. So if I end up with water-based solutions and a gas is a product, this is also categorized as a gas evolution reaction. Okay, so let's consider reacting hydrochloric acid with potassium carbonate. So first of all, I'm going to write the molecular equation of the gas evolution reaction, and that's actually a two-step process. So I'm going to go ahead and take the hydrochloric acid, react it with potassium carbonate, and what we should recognize is that we have a strong acid here. Now, you will need to learn that the carbonate ion can act as a weak base. So my carbonate ion can be a weak base. Since it's part of an ionic compound here, we still classify it as a strong electrolyte, as a soluble ionic compound, even though the carbonate ion is a weak base here. Now, since the carbonate ion is acting as a weak base, we can accept protons from the acid. And in fact, we're going to accept 2 protons from the acid to form carbonic acid. So we basically produced from the strong acid, hydrochloric acid, and the weak base, the carbonate ion, a weaker acid. So we can sometimes do that. Strong acids can sometimes protonate bases to produce weaker acids. We end up here forming a soluble ionic compound where the potassium cation is from our weak base, our chloride ion is from our strong acid, so we get potassium chloride, which is soluble, and we end up with carbonic acid. Now, carbonic acid here that I've labeled in yellow is unstable. It can go through a decomposition reaction. So since the carbonic acid can go through a decomposition reaction, the second step of this process is the carbonic acid decomposing, and I show a double set of arrows. Now, usually when I write this on paper, how we'll show double arrows is with a single head to the arrow, and we'll use this notation. I just wasn't able to easily add that notation onto the PowerPoint. Now, if we end up seeing the carbonic acid decomposing, what it decomposes to is carbon dioxide gas, so there's going to be bubbles occurring from this solution, and we end up with H2O water. So I show a phase label of, since I'm in a water-based solution, of just an L for water. So I can expect whenever carbonic acid is present, it's an equilibrium where I could form CO2 gas, carbon dioxide gas, and water. Now this is reversible. For example, if I bubble carbon dioxide gas into water-based solutions, we can form a little bit of carbonic acid. In fact, that's what happens in your everyday soda pops. Your soda pops with the carbonation, you bubbled CO2 in there, you end up with carbonic acid. Usually you have them under pressure. When you open up your soda pop can or your container, you end up with this equilibrium shifting back to the right. Some of the carbonic acid you had formed decomposes. You end up forming some carbon dioxide gas that escapes from solution. And so that's a process that's going on. This reversible decomposition reaction is occurring in soda pop in your everyday life. Basically, whenever carbon dioxide is dissolved in water, we can have a little bit of carbonic acid. So here we just happen to force the carbonic acid to decompose. We tend to favor shifting the equilibrium to the right from the strong acid that's present. Now, if I want to write the overall reaction for the two steps here, the overall reaction will show me that I end up forming potassium chloride as the first product here. But since the carbonic acid goes through a secondary reaction, I show that it basically has canceled out. So I formed carbonic acid, but then I consumed it through the decomposition process, so I've canceled it out as I added up the two steps. And I show the products of the decomposition reaction instead, so I show that I formed carbon dioxide gas, and I show that I formed my liquid water. So this is the overall process. So it might be a little bit harder to tell that there was a double displacement reaction like in the first step and decomposition in the second step unless I think about the individual steps. Okay, but the overall reaction is as shown. Now, that's my overall reaction. What would be the net ionic equation? Now, the net ionic equation, my strong electrolytes would be my strong acid, hydrochloric acid, my soluble ionic compounds, my potassium carbonate, my soluble potassium chloride. I'd break those all up into ions, but my non-electrolytes would be my molecular compounds that are not strong acids or strong bases. So I'd end up with having to keep my carbon dioxide and my water. And I'd see that the only spectator here would be from the chloride ions from the strong acid, which are still chloride ions in the soluble ionic compound at the end. And my other spectator ion would be the potassium ions I began with and the potassium ions I end up with. So what I would find then is the net ionic equation shows that basically any strong acid mixed with any soluble ionic compound that has carbonate ions would form carbon dioxide and liquid water. So all I did here was I skipped over the total ionic equation and removed the spectator ion. So if you wanted to stop and write out the total ionic equation, you see potassium and chloride ions were spectators, and they aren't shown in the net ionic equation. So practice doing this, practice being able to do this before the next exam. Okay. Now we've been able to see gas evolution reactions as well as acid-base neutralization reactions. We've applied writing net ionic equations to precipitation processes as well as writing them for acid-base neutralization reactions. Let's look at a few more examples of acid-base neutralization reactions. So let's write a balanced net ionic equation for the following reaction. We're going to show sodium hydrogen carbonate. Now remember, sodium hydrogen carbonate is also called sodium bicarbonate. We're going to show that reacting with acetic acid, which is present in vinegar. So you could use this as a reaction basically where you have vinegar and baking soda. So sodium bicarbonate or sodium hydrogen carbonate, that's just baking soda. So it's vinegar and baking soda. This is what you might have used when you were younger with a vinegar and baking soda volcano maybe for a science demonstration. So let's look at the reaction for this. If I look at the molecular equation, this is going to be a gas evolution reaction. Let's see how. We're going to have acetic acid, and we have hydrogen carbonate, also known as the bicarbonate ion. Now, the bicarbonate ion, just like the carbonate ion, is slightly basic. So the hydrogen carbonate is almost halfway through the process in a sense compared to the carbonate ion. We have one proton, one hydrogen already associated with it. So I only need one equivalent of protons. I just need one acid molecule to donate another proton to the bicarbonate ion, to the hydrogen carbonate ion. If I do that, I end up forming carbonic acid again, which can decompose, and I can end up with carbon dioxide and water vapor. So basically what I'm saying is if I have an acidic proton here, and I have the hydrogen carbonate ion, in a situation like that, we can end up forming carbonic acid again. And so whenever I see a possible product of carbonic acid, I'm thinking to myself, well, carbonic acid is somewhat unstable and can go through a decomposition process, especially in the presence of acids that I've been adding, and so it should decompose and I form carbon dioxide and water, just like we saw happen before. So just remember, whenever I see a salt that has either carbonate or bicarbonate, we can form carbonic acid, then form CO2 and water in a gas evolution reaction. Okay. Now what I want to do next is write the total ionic equation. So I need to recognize my strong electrolytes. My strong electrolytes will be my soluble ionic compounds, and any strong acids or strong bases. Now be careful because acetic acid is a weak acid. So the major form in solution is HC2H3O2. That's the major form. Only a very small percentage of acetic acid is forming protons and acetate ions. Since the major form here, so I'm going to write MF for major form. Since the major form is the molecular form for the acid, we do not break it up. Now on the product side, sodium acetate is a soluble ionic compound, so it's going to be a strong electrolyte, so I'm going to break it up. Carbon dioxide and water, those are molecular compounds that are not strong acids and they are not strong bases. So they're non-electrolytes, so they do not get dissociated into any ions. We do not show any ions forming there. So for the total ionic equation, we write down the weak acid together still in its molecular form. We write the soluble ions from the sodium bicarbonate. Then for our products, we show the soluble ions from sodium acetate. And then we show our non-electrolytes, our carbon dioxide, and our water together. Okay, so now I can only cancel out my spectator ions are the same on both sides. So sodium ions are the same on both sides. But you notice that the hydrogen carbonate ion isn't on the right-hand side as written, and the acetate ion isn't written the same way. The acetate ion here in the product side is part of the major form of the weak acid, the acetic acid, so I cannot cancel out the acetate ion in this case. So if I write the net ionic equation, we end up with the acetic acid reacting with hydrogen carbonate. We end up forming carbonic acid, which decomposes into carbon dioxide and water, and we leave the unprotonated acetate ion behind since its protons has been transferred to the carbonic acid, which went through decomposition. So this would be the correct net ionic equation. That's about as challenging as the net ionic equations can get in the course when you have to consider decomposition as well as part of the process. Okay, so at this point, I want you to continue practicing some of the additional equations that I have in the slides here for this process. Look at some more gas evolution reactions, look at some more net ionic equations, continue practicing this process. I very likely will post some additional practice videos on how to do this, but continue on writing net ionic equations. I usually put several of these types of questions on the NETS exam. I often will show some of these with precipitation reactions and some of these with acid-base neutralization reactions, and potentially at least one with a gas decomposition reaction included in it. So make sure you practice these with your classmates as well as your local instructor. Thank you very much.